Question 6 says, use the alternating series test to show that each series converges. In part A, we're looking at the sum of -1 to the n over n, and n starts at 1. So expanding, we get -1 plus a half minus a third plus a fourth, and so on. Okay, so note that this is the alternating harmonic series that we looked at the end of the last video, except here we're starting on a negative, and then a positive, then a negative, and a positive, and so on. So in fact, this is the negative of the alternating harmonic series, and so should converge. Now, don't worry that this series is starting on a negative. Okay, the point here is that we can apply the alternating series test provided we have true sign alternation from term to term, which we do have. And to apply the test, well, b sub n is 1 over n. And since 1 over n is clearly a decreasing sequence, the first condition is satisfied. And 1 over n clearly goes to 0 as n approaches infinity, so the second condition is satisfied. And so we conclude that this series converges by the alternating series test. All right, part B. We're looking at the sum of -1 to the k plus 1 times 2k over k squared plus 3. And here k starts at 2. So expanding, we have -4/7 plus 6/12 minus 8/19, and so on. Okay, so here b sub k is 2k over k squared plus 3. And it is true that this is a decreasing sequence, but it takes a little bit of work to show that. So to show this, okay, let f of x be 2x over x squared plus 3. And note that its derivative in simplified form is 2 times the quantity 3 minus x squared all over quantity x squared plus 3 squared, and this is negative on the interval from 2 to infinity. Okay, and that's because this expression here in parentheses in the numerator is in particular negative on that interval. Okay, so since the derivative is negative on this interval, f decreases on that interval, and so the sequence b sub k is decreasing. Okay, so that's the first condition. Now the second condition, that b sub k approaches 0 as k approaches infinity, is also true. And loosely speaking, that's because the numerator is linear and the denominator is quadratic, and the quadratic is winning the race to infinity. So now, to make that a bit more precise, I'll divide numerator and denominator by k. So this is 2 over k plus 3 over k. And here k is approaching infinity. 3 over k is approaching 0, so this denominator is approaching infinity, and so 2 over this expression will approach 0 as k approaches infinity. Okay, so the second condition is also satisfied, and again we conclude that this series converges by the alternating series test. Okay, so now let's check out part C. We're looking at the sum of -1 to the n minus 1 times the natural log of n all over n, and n starts at 1. Okay, so here's first few terms. Okay, also note that the natural log of n, okay, this is positive for n greater than or equal to 2, and the natural log of 1 is 0. Okay, so these b sub n's are all non-negative. Okay, and it is true that this is a decreasing sequence, except that it's decreasing for n greater than or equal to 3, not for n greater than or equal to 1. So let me show you a visual here. So here is our sequence. And see, we start at 0, and then it goes up to about 0.3466, then up to about 0.3662, and then we start to decrease. Okay, so is that a problem? Well, no. Just like what we saw with the integral test, as long as the sequence is eventually decreasing, okay, we're going to be okay. And so the reason being, right, is that if I can show that the series starting at 3 converges, okay, so in other words, this tail end converges, then as we've seen with what we call the tail end property of series, right, this original series will also converge. All right, so how do we actually show this is decreasing? Well, just like in the last part, okay, just show that this function f of x, which is log x over x, is decreasing by showing its derivative is negative on this interval. And that is true because f prime of x in simplified form is 1 minus log x all over x squared. And that is negative on this interval from 3 to infinity. Okay, so the sequence is decreasing. That's the first condition. For the second condition, it is true that b sub n approaches 0. Now, to compute this limit, we have to use L'Hopital's rule, because note that natural log of n and n, right, these are both blowing up. So we have an infinity over infinity indeterminate form. And so I apply L'Hopital's rule. I take the derivative of the natural log of n, and that's 1 over n. And then I take the derivative of n in the denominator, and that's just 1. And as n approaches infinity, 1 over n goes to 0. And so, yes, b sub n does approach 0. So the series converges by the alternating series test. All right, so then for the last part, we're looking at the sum of the cosine of pi k over k cubed. K starts here at 1. Okay, and as we've noted previously, cosine of pi k is really just negative 1 to the k, right? Because if I plug 1 in, I'm going to get cosine of pi, and that's negative 1. If I plug 2 in, I get cosine of 2 pi, which is positive 1. And then it's just going to alternate in sign. Okay, so this is an alternating series. And here we have b sub k is 1 over k cubed. Clearly a decreasing sequence, so the first condition is satisfied. And for the second condition, well, 1 over k cubed, clearly it goes to 0. And so we conclude that, again, the series converges by the alternating series test. Great, and that's going to do it for this video.